We got two more. We're going to talk about the rock cutting in much more detail to get a better understanding of different aspects of things, in particular bonded particle modeling. And then we're going to talk about, you're going to learn a little bit about roadways and ballast underneath roadways. So this is a rock cutting test. There's the cutter, 13 millimeter diameter. It's held in a chuck. It's very rigid. This is sandstone. It's called Torrey Buff sandstone. It has a 50 micron grain size. So it's very, very fine grained. This comes from a quarry in Utah, and this sandstone is used by companies to do these tests. It's become a standard. And this is what this looks like. So this thing, here you see it's plowed out. That was a previous scratch. So this is going to be lowered, and then it's going to be moved forward at a fixed depth. And you can't hear this because we're doing this virtual thing, but there's sound with this too. And what you're hearing is a whole bunch of cracking and popping because this is a very brittle type of mechanism. Okay. So of course, what do we do if we want to model this? We're going to make a synthetic rock. This is actually plexiglass pellets that are near spherical that were poured into a cylindrical shape cup, and then they were cemented together with some kind of weird chemical process. They heated this, and then where they were touching, they got cemented together. Okay. We're going to create a particular type of synthetic rock where we use what's called a parallel bond, which is a type of contact that resists moment. And the parallel bond is going to behave very much like this type of a physical system. Remember, about any PFC model you built, you could in principle actually create in the real world. This is glass beads that have been cemented with epoxy. And you see how there's like a circular cross-section cylinder of cement. See how this one, it broke? And there's varying amounts of cement. This cement diameter is much smaller than the cement diameter here. In fact, these actually are filling all the space, okay? The parallel bond model is mimicking this type of system. So it's behaving like a hunk of cement that has a cylindrical circular cross section. It also has a parameter for the width, for the diameter of this. So here it is, 2R bar. And what this is trying to show that this is one of the grains, this is another grain. This red surface is kind of like a hunk of surface of cement that's connected to the top. The green is a hunk of cement that's connected to the bottom. So when the bottom moves, the green moves with it. And when the top moves, the red moves with it. Notice that this thing, if I pull it, it's going to sustain tension. If I rotate it, this part's going to go in compression. This part's going to go into tension. Therefore, it can resist a moment. So this thing is resisting both force and moment. Okay. It initially is linear elastic when it's bonded. It would be like this if you just did small strain. It's be like linear elastic, but then it can break. And when it breaks, the bonding, the cement is just gone. And now it behaves like two spheres that are just interacting frictionally. Okay. And we're going to talk much more about this. This is an example of a type of material we can build. We're going to build parallel bonded systems to behave like well-connected sandstones. Okay. And then what we're going to do is we're going to make the cutter and we're going to drag it across the rock and we're going to monitor the forces on the cutter and we're going to look at the damage in the rock, right? And this is talking about drilling mud, producing pressure on the bottom, and we're going to mimic the effect of drilling mud by using, this is our schematic of our model, right? There's the cutter at a fixed depth of cut D at a fixed rake angle. And we want to apply pressure. How are we going to apply pressure? We're going to write a special algorithm that I call a chaining algorithm. We're going to start here, find a particle. We're going to then go counterclockwise to find the next contact with an intact bond. And then we're going to go find the next one. So we're going to end up traversing the surface of this We're going to store those particles in a list, and they're going to be made green. And now we know this. Now we've just created a membrane, and the membrane has shape. And so given a macroscopic pressure, we can just look at the two sides of each particle. We know the orientation, and we say there's an applied force on the particle. The red is the applied force. So that applied force is going to basically be mimicking like a membrane stretched on top. And we keep reestablishing the chain as the simulation proceeds. And of course, once this guy starts to go here, there has to be a chain from the bottom all the way to there. And so this is what we call a chaining algorithm. We do this in 2D. We can also do a different thing in 3D. We'll talk about that later. What do we see when we're doing what they call dry cutting with no drilling mud? We're going to push that across, and we see these chips forming. And this is the force distribution in the system. And we're looking at the old PFC 4 systems. I did work with them long ago, and then I did more work with them more recently. So these were the old models. You can see the breakage, and you can see the force distribution. Again, blue. Stop. How do I stop it? Black and red. Blue is compression in the grains. So notice where it's all broken, there's just blue because it's just loading the grain surfaces. Black and red are compression and tension in the cement. All right. And if we look at a more modern rendering, now that we had PFC 6 in 2018, 19, I did this work, I think. Now we can, of course, build bigger systems with more discs, and we can see, and you can clearly see the cement is drawn as black lines, and you can see how there is this granular broken material that's being forced through the flow underneath the cutter head. Okay. And then here's the forces on that. Sorry, stop. That's the wrong one. Here's the forces on that system. You can also notice how the forces build up, and then there's a breakage, and they go to zero. And then they build up, and then they go to zero. This is the brittle nature of this system. The forces get high, and then they go to zero. It's just like if you had a layer of ice, but outside my house, half the year there's ice. And if you shovel the sidewalk with the ice, you take your shovel and you push it against there, and it you push it, big load builds up, and then it goes crack, and then you go forward a little, and another big load builds up, right? So this is what we see in these systems. Oh, wait. So for the wet cutting, let's just look. This is an animation of the wet cutting. And you can see all this broken material. And because there's pressure, there's that chain causing pressure, it's inhibiting the chips. And so instead, you're getting this material to ride up the face of the cutter. This big shear thing just forms here. Watch, as it goes farther, eventually it's going to break this rock up here. How is it going to break? Let's see. Now here, this cemented rock is getting broken. It's just kind of pushing this thing forward. There, it's trying to go down. Okay, there we go. Stop this. All right. We can do the same thing in 3D. That's what the schematic of a 3D system looks like. Now the cutter is actually a proper disc. We developed another algorithm to apply pressure to the surface of a 3D system. This is a very complicated problem. Developed an algorithm called the shining lamp algorithm. This was all implemented then in fish. Here's the example. There's a bonded assembly. That's a sphere. This is 3D, okay? And we're just looking down the global axis at one sector of the sphere, okay? What we do then is we say, pretend that there was a bank of lights oriented perpendicular to the x direction, infinitely far away, that was shooting rays of light in the x direction. And we're going to find where those rays of light intersect the surface. And then there's going to be light coming from here and light coming from there. So this is what that looks like now. This is going to be dependent upon, there's like a light grid, if you will. So the size of the grid cells. So you can see from the red direction, that's where the red light is hitting. That's where the blue light is hitting. And as we refine the grid size, we start recovering very nicely where this is. So we're essentially painting on light from different directions onto the surface of each sphere. Then what we do is take the area of all the red and we apply a force that area times the pressure, and that acts in the red direction, and in the blue we do the same thing in the green. This algorithm keeps running as the surface evolves and as this breaks. This is our way of being able to apply pressure to this evolving system. When we do that, this is what we see. This is blue is particles that have had all their bonds broken. And so it's pretty cool because what it's doing is plowing out a broken area, but it's not going any farther down, and it's riding up the face. I don't have any more fancy images because this was the client then using what I did here in 2013 and doing this type of modeling. And this is one of the plots that he created. So it seems to be making sense. Okay. This is talking about once this thing reaches a steady state, the cutter is always pushing against broken material, and that broken material is flowing beneath the cutter, and you're seeing very, very different behavior by just a change of boundary condition, which is what you expect. Again, the forces, here's a good one of the forces flowing through the broken material. Blue is surface compression. Black and red is loading in the cement. Okay. So actually the overall resistance, the mechanical response, is controlled by not only the properties of the virgin rock, but it's also controlled by the properties of the broken material that's being compressed. Okay. This is a whole nother aspect of this system. Their original modeling they all did was with continuum codes, and they just kept trying to change the properties of the virgin material. And they weren't getting very good comparison. Here now, there's a whole different set of properties, which is this broken material, which is they believe is what's really happening in the system. So here's looking at a couple of slides. Here we're going to visualize this in two different ways. This is just showing every disk as a yellow thing, and these are those broken bonds as red for tensile breakage and blue for shear breakage. And this is visualizing it differently. This is drawing a little tan line between the intact cement. Okay, and it's not showing the yellow. So here you're pulling out the cemented fragments. Here you're actually showing all the discs. And so the question then becomes, notice what's the mechanism that's going on in here. Okay, we need to be able to recapture that mechanism. And the big important mechanism here is that the results are sensitive to this chamfer. So therefore, you're going to model this. You need to have at least a certain number of particles across this chamfer, because if you don't, that means the particle system doesn't even feel the chamfer, right? And so how do we choose this? So here's the first level way of thinking about how do you build these synthetic bonded systems, right? Well, you want to be informed by the actual grain microstructure of that rock, right? So here you can see 300 microns, very small grain sizes. And so it's mostly quartz, and the pores have blue epoxy. Every time I look at a scanning electron micrograph of a rock, I always get queasy in my stomach because I realize it's far more complex than these models we build. So here's the case. Here we go. These are the grains. They're packed. They're yellow. We're drawing them a little bit smaller at 80% of their true size. And here's this cement, the parallel bonds. And we're drawing them then as these tan things, right? That's how we produced those plots before, okay? Notice that the grain size is 50 microns. So ideally, we would like to make a bonded system, and we're going to say each grain is a disk. And so we'd like to make those grains be about 50 microns too. And you're going to see we do. This is the correlation. This is 300 microns. This is 300 microns. So this is the system we're building, okay? As you're going to see also, we're going to build a series of models that have bigger and bigger and bigger grains, because in most cases, you're not able to directly match the grain size, and you have to make bigger grains. And what we're going to find is that we're going to get pretty much the same macroscopic response even when we have bigger grains. So here's the system we constructed The only thing different here is the grain size of the discs. This is the average grain size. That's the 50 micron. This is the 100 micron, then 200 micron. This again is a 1 millimeter chunk, right? So you can see bigger guys, bigger guys. This is the actual grain size, okay? And what's important is the number of grains. I'm postulating that what's important is the number of grains across that chamfer. How many grains are across that distance? And I'm going to call that the resolution. I'm going to call that the cutter resolution. The idea being, what is the resolution of the material that can resolve the cutter? So it's the number of grains across the width. So you can see this one has 17 across, 9, and 4. And I didn't want to go any bigger than that because that wouldn't have made any sense. So the next question is, because this is a simplification of the true microstructure, which it pretty much always is when we do this modeling, we have to do calibration, right? What's calibration? Calibration is taking a model, measuring some macro response from the reality, measuring that response, and then essentially adjusting the microstructural parameters to try to match that, okay? And the typical things we try to match when we do representations of rock is weak in tension, so we want to match the tensile strength, and we want to match the behavior under confinement, and not only UCS at 0, but confinements here, like results of triaxial tests, right? Because as you know, the amount when you apply confinement to rock, it gets stronger, and the amount that it gets stronger can be related to the internal angle of friction, they call it, right, of the rock, you know. Okay, so we try to match those things, okay, and for this particular system, we use these parallel bonds, and what we find is that if we match the tensile strength, which we can do, we're going to underestimate the compressive strength, okay? So what we can do with this is we're going to build a model. So since we can't match both, we're going to have to choose. So I'm going to choose to match the tensile strength because I believe it's the tensile strength that's governing the formation of those chips, okay? So we're going to match the tensile strength, the Young's modulus, and Poisson's ratio of the actual sandstone, and we're going to underestimate compressive strengths. Now, just as an aside right here, this was using the parallel bonded material. It is a known limitation of the parallel bonded material that the ratio of compressive to tensile strength is going to be too low for that material. There's dozens of papers back in the late 2000s of people trying to figure out why and trying to figure out how we can change the properties we give to the parallel bonded system in order to try to increase compressive strength relative to tensile strength. And no one could do it. And eventually we figured out why. And then we built a new contact model, which we call a flat joint contact model. And with that contact model, we can match the tensile and compressive strengths. And that's all that I want to say at this point, because we're going to talk much more about that later, okay? But at the time of this work, we didn't have that. And so I said, well, best we can do is use a parallel bonded material and we'll just match the tensile strength, okay? So we do this, we choose a set of micro properties so that we match the tensile strength and the modulus and Poisson's ratio. And what we find is we then just vary the grain size, because remember, we built these models with different grain sizes. And for all of these 3 different grain sizes, we still get the same macroscopic response. Same micro properties. The only thing we're varying is the grain size. And you're able to still get the same tensile strength and Young's modulus and Poisson ratio. Okay, that's an interesting and important point. For these types of things right here that we're measuring, this is independent of grain size. This is in general what we see when we're measuring UCS, triaxial, and tensile strength of these bonded assemblies. The basic thing is we need to have a sampling that's like a representative volume. Think of it that way. And the more particles we have in there, it's still a representative volume and it still has the same macroscopic response. Okay. And what we're going to find is that at the laboratory scale, when we match UCS and tensile strength, we can choose micro properties so that we're scale independent, we're size independent. Particle size doesn't matter. But when we apply this at the macro scale, for example, at a tunnel, and we want to look at damage that forms in the roof of a tunnel, what we're going to find is that there's going to be a size effect, and the strengths that we get are going to be dependent on the particle size. And what's that indicating is that there is some sort of a scaling that needs to occur when you work at the grain scale of the actual particle size, and then when you scale up the size to model an excavation. Because when we model an excavation, we're not able to have 50 micron grains, and we have to scale everything up. And that macroscopic things that we're measuring, like the strength of breakout, we're going to find that the breakout strength is going to decrease as we decrease particle size. Okay, even though for all the different particle sizes we measured the same UCS and the same triaxial values and the same modulus and tensile strength. Okay, that's just a precursor to what we're going to end up talking about more as we go through the course. Now, here's the question for you. I'm going to argue that we cannot expect to get a quantitative match in this 2D test. And why is that? Any ideas? Think about the question is, what is actually a 2D PFC model compared to a 3D? 3D model is really spheres, really packed in 3D space. That should really behave like a true 3D thing. The 2D model is this. 2D model is unit thickness cylinders. Okay, it's just unit thickness cylinders. And when we put that wall there and drive it across, what we're really doing is that wall, we only see these segments, but really conceptually that wall is mechanically behaving like a unit thickness thing like this. And so we're basically have a bunch of cylinders glued together and we're pushing them with this. This is totally different than the actual physics of the real 3D thing, of the spherical particles. Okay, so for this particular problem, the best we can hope for is kind of like a qualitative comparison, so that we can have a qualitative, we can find what's the energy to cut with this system and how does it depend upon if we change the angle or how to change other things. But at best, it can be qualitative. Okay, that's an interesting, important thing. This is again illustrating, these are actual discs, which you can, cylinders, which you can hold in your hand. And these cylinders have a size distribution. And if you hold them in your hand and squeeze your hand around them, what you'll find is the small ones tend to fall out. And that has to do again with the force chains. And the small ones tend to get surrounded by bigger ones and the load gets carried through the bigger ones. Why do I have these? I have these because someone was trying to better understand the behavior of a PFC 2D system. And what they did is they got a whole bunch of these discs. They laid them and stacked them together between two plexiglass walls that they could see through. And then what they did is they put a pile in there by putting like a big wooden thing in there, and they put the discs all around it. And then they, loaded the pile and they looked at the deformation field of the discs. And that's what these discs were used for. Okay. I use them as an illustration of that is what a PFC 2D model actually is. Okay. So then what we did is we said, what's the effective size? So we built 3 models, as you say here, with the different sizes. And this is the boundary condition, the boundary value problem we did. Notice it's a small thing, 24 millimeter length, 4 millimeter height. We're going to take that sucker at a given rake angle, at some velocity, and at some depth of cut and moved it across. Also, the velocity is irrelevant in our models here because we're running this in a way so that it's quasi-static. So actually, it's as though this thing was moving infinitely slowly. We're basically, as the damage forms, we're going so slow that we're allowing time for all the forces to redistribute. Okay, so that it's quasi-static. Now we're going to look at this for the different grain sizes. So here's the case with the grain size of 50 microns. Okay, and as we go, and again, we're going to draw this in 2 different ways. Yellow is going to be, we're going to use yellow for the grains. We're showing all the grains here. and we're going to do red for the guys that have that are close, because there's like bonds that have broken between here and here, but we don't want to see all those crazy red guys in there. So we're only going to show the micro cracks where the gap between the current parent particles that broke is small. Okay, so here we're seeing the particles. Here we're seeing the cement. Remember, I was drawing the cement like this. So this particular way of visualizing, when you do it this way and you shut down the yellow, is going to look like that. So it's going to pull out the part that still has intact cement. Okay. And so here, after you go this far, here's the damage. This damage is interacting with the boundary, which means our boundary is too close to do this. Again, I developed this for this company, and I could only do a few quick demonstrations, and then those guys have taken it and they're doing all kinds of runs with it. All right. Here is what you get out of these models. This is the force as a function of cutter displacement. This is the total force acting on the wall. And so for a wall, this is PFC, 3 walls, 1, 2, 3. There's a whole bunch of forces pushing against the wall. I can ask PFC to sum up all the forces acting on a wall and give me a resultant force and a resultant moment. That's what I'm looking at, is the resultant force. And I can resolve that into the resultant force in the X and the resultant force in the Y. And so notice it's a brittle thing. Force builds up, breaks, drops to 0 almost, builds up, okay? We can take a running average of those forces to come up with what we'll call the average cutting force. And then we can basically integrate that force through the distance to come up with the energy to remove a unit volume of rock. And we basically only do enough displacement till we reach a steady state. Okay. We can also monitor all of the energy sinks in the entire system because we have a model. And so let's just talk about this a little bit. This black line is the measured energy input by that wall, because the cutter is a wall and we give it a velocity and we keep on integrating the force that it pushes with over the distance, and that's the work done on the system. So the black one is the work done on the system that we're monitoring. We can get an average work by drawing a straight line. Okay, so 21 watts was put in there. Then we can partition that energy. Where is that energy going? Okay, so some energy is just strain energy. When a bond is a spring, the spring breaks. Whatever strain energy was in there is removed. So there we go, bond broke, strain energy got released. Sorry, that's this blue, the kinetic energy. As the bonds keep breaking, the breakage, the strain energy keeps accumulating that we're removing. It's very negligible. Then there's kinetic energy in the system. So that you get these spikes, because when a thing breaks, it sends out a shock wave. It sends out a compression wave, actually, and the whole system goes, and that wave goes out, hits the boundaries, comes back. Now, we have to have damping in our model to remove that kinetic energy. And we'll talk about this when we talk about the physics of PFC. We have a damping mechanism that we use. It's very good at removing all that vibrational energy in the system. And so that's consuming energy. But then most of the energy is actually going on frictional slip between either the two surfaces of the particles or between the particle and wall. Because remember, the particles are getting split across the wall. As you will find out, the simple contact model we're using here has a property which is the friction coefficient. And that friction coefficient is the friction coefficient between two surfaces. And what it's doing is it's limiting the shear force that can be sustained, because it's friction coefficient times normal force. And we're going to talk a lot about that tomorrow. But the sum of all of these things equals the energy input to the system. And so what you see is a huge amount of energy is going into the slip. It's not breaking the bonds. That's a small amount of energy, the strain energy in there. It's mostly this grinding, this slip between material. And then if we look at the slip, we can partition that into the slip between the particles and the slip at the interface with the cutter. And if there's not much going on, there's not much dragging going on there. Mostly it's that granular material being forced to constantly rearrange and frictionally slide. This is also a very interesting thing. This clearly would also be why that thing must heat up like crazy. It must get really hot in there. This is, again, the broken material is made up of unbonded grains, and that's the thing that the cutter is pushing against. Notice the forces. The cutter bears up against this. These are the forces flowing into the material. This is all broken. High forces at a few force chains, that then dissipates into more uniform forces in the bonded system. Here we go. We take this thing and we push it a little farther, and suddenly, presto, the forces go to near zero because there's this brittle breakage, and then this granular system rearranges itself. This is actually going the other way. This is a displacement of 11.2, no load. We go a little farther, the load builds up. We go a little farther, it goes down to zero. This is why you keep getting this buildup, localized damage, stress redistribution, just like in the real system. Here's the key point. The top point is super important. Why are we building this model? That's the most important thing you always have to ask yourself. What do you expect to get from the model? Well, what we expect to get from the model is the proper energy to cut, okay? So this is the system with the 50 micron particles. This is the system with the bigger particles, double the size. And this is the system with the really big particles. The energy required to cut is almost the same for all of these three systems, which means that we could probably get away with doing a whole bunch of parameter studies with this bigger system, and then maybe occasionally do some models like this just to confirm that we're getting the same answers. Okay. Of course, we want to do that because it takes a lot more runtime. This was also in 2018. The code runs faster now, but yeah, it was a hell of a lot. And notice that only went 11 millimeters, not even the 22. So this is an important thing. And so this is what we find. This is what we almost always do when we build these systems. You make a collection of different sizes. And the way that you're going to have a well-defined set of fish functions you're going to use to create your materials and to test them, to do the UCS and tension tests. And the parameters that you're going to assign to run that stuff, one of them is going to basically be a parameter that's going to scale the size distribution to make it either uniformly bigger or uniformly smaller. So you're going to be able to build synthetic specimen, do a bunch of tests on it, go back, change the size by this one parameter, and then run it again. And you'll be able to easily do a set of tests with different sizes to see what effect that has. A couple points about this pressure application business, which is, in the end, that's really that's the real cutting they care about. This is this chaining algorithm again. Okay, it's walking the surface, identifying a connected chain. Notice this chain now can go all the way around here, and the cutter pushes against it, right? We find these particles in the chain. We apply an external force to each of them based on the orientation of the chain. Okay. This is what this starts to look like. You get this mass of broken material riding up the face. This is looking at how the load is distributed in that system, right? Very high compression down here. Okay. This is the model where we make different colors, and you can see how it's pushing up, and it's kind of forming a shearing thing here, and you got these different layers that have pushed up. This is a schematic from a paper where people are describing what is happening when you do cutting, and it's the same type of thing. You basically keep shearing off layers, and then they keep getting and riding up. So this is a confirmation that we have a reasonable model here that seems to be producing some of the basic mechanisms that are occurring during the cutting. So again, dry, wet. This you could describe this as brittle. You could describe this as plastic-like. There's the dry cutting. There's the wet cutting. Okay, you've seen this. Here's the key element. This is the forces on the cutter, and these are at the same scale. Okay, and notice how the brittle case, it loads up and then it goes to near zero. Notice that when you have confinement, it's still got a brittle component, but it tends to be, notice it doesn't drop down to zero, which to me makes a lot of sense. These forces, sorry, they're not the same scale. This scale is 10 times bigger than this scale. So you can see that the force to cut is about 10 times larger. And again, you got the fluctuations, which are like the brittle part of this behavior, but there's an overall, it stays compressed because of that confinement, which again makes sense. Here's the energies. You can see in this case, 58% is in that grinding of the granular material. This is the dry cutting. So the slip, the grinding of that material, 58% of the energy. When there's wet cutting, almost all the energy is the grinding of that material. That's pretty much all the system can do. It's just being held together and it's turning into a granular mass. One of the interesting things, the client says, he shows me these cuttings after the thing is done, and what you get these ribbon-like things that are made up of broken up sandstone that's been almost like reconstituted and squeezed, and you can hold it. It's very brittle. You drop it and it like breaks in pieces. So this, it seems to be making sense, this mechanism where you're basically, but in this case, we don't have some scheme in there that says, oh, you're all a big mass of things and now we're going to bond you together to make you stick. Obviously, as you understand, you could do that. The other power of this modeling scheme is that you're taking steps in time. So at any instant, you know everything. And at any instant, you can say, okay, now put in more cement and continue with the simulation, right? And people do all that kind of stuff as well. You might have healing, for example, where over time the cementation returns, for example. Here's the final set. The key point is we've convinced ourselves that we have the proper mechanisms in the model. If you do, you can use it to perform parametric studies. Again, these are qualitative studies with the 2D version of this model, right? And as I said before, it's giving you a link. You can change the rock microstructure, you can change the cutter geometry, you can see what effect it has. Okay, so that's the idea.